Okay, so welcome everyone. I think I will make the usual welcoming announcements at the end of the talk because there are still some people arriving. So let's start right on time with Petar telling us about 5-point functions.
Can you hear me well? Okay, of course, I would like to start by thanking the organizers for making this wonderful event happen and for giving me the opportunity to speak here. So today I want to tell you something about 5-point Bootstrap, and this is also the title of the paper that I have written earlier this year together with Valentina Prilepina and David Poland, and some parts of my talk will be based on a work in progress that we are doing right now. So this is a rough outline of my talk. I'm going to give a motivation for studying 5 and higher point functions in general. Then I'm going to introduce 5-point correlators in CFTs with all details about notation, conventions, etc. Then I'm going to discuss 5-point conformal blocks. In particular, I'm going to show you a new way to compute these conformal blocks, and I will discuss how this new way is superior in some aspects with respect to the previous ones. Then I will apply this technology to mean field theory, and in the end, we'll apply this technology to do some numerics, in particular in free scalar theory and free decriticalizing model. So you might be wondering, why do I even bother telling you anything about 5-point functions when we know that in principle we can bootstrap all CFT data from 4-point functions? And the reason is that, well, even though in principle we can do it, in practice that's pretty hard. So what we do in practice is the following thing. So in practice we consider correlators of 4-point correlators of external scalar operators, and then we take some OP expansion, and then we can write this 4-point correlator as in this way, where we sum over all primary states times conformal blocks of dl. And then when you consider correlators like this, you actually see that the type of OP data that you can access through these types of correlators is basically a set of primary operators which are all symmetric and symmetric and traceless representations, since you have the OP between two scalars. And also you can access the OP coefficients of 2 scalar operators and 1 spinning operator, where spinning operators is in the symmetric traceless representation. But this is not the end of the story for pretty much any CFT. But all CFTs have other types of CFT data. And for example, they have non-zero OP coefficients of this type. Here I'm just writing correlators in 3D criticalizing, but this generalizes to pretty much any CFT. So this is the OP coefficient where two states are spinning. So this is stress tensor, again symmetric traceless representation, and the third operator is a scalar. Then you can also consider OP coefficients of this type, where all three operators have non-zero spin. And then finally, you have operators in anti-symmetric representations. Now, if you want to access these types of, this OP data, and of course their OP coefficients, but if you want to access this OP data through 4-point functions, you would have to do a bootstrap of correlators like this. Etc. So, and as far as I know, at this moment, there are at least 2 groups that are trying to do this. So it will be very interesting to see what results they get and how they compare to our results. But in practice, this is hard to do, and it's very hard to obtain some bounds from this type of from studying these types of correlators. So instead, what we do, we consider, again, an example, 5-point correlators of external scalars. And when you do the OP in this type of correlators, you can represent this OP by the following pictorial representation. So there is really only one topology of the channel expansion here, and then you can have so here you can exchange some symmetric traceless operators of non-zero spin. Here you can exchange again, symmetric traceless operators of non-zero spin. So this OP coefficient is this one. This one here is also of this type, but this OP coefficient here, you actually have access to OP coefficients of where two operators are spinning operators, and the third one is a scalar operator, and there is an index Nij. So this is a type of CFT data that we can access by studying 5-point correlators. And this type of CFT data, we didn't have any access before. So then if you want to go to the other parts, you should study 6-point functions. These anti-symmetric representations are also going to appear in the 6-point function, so you might be able to say something about them. And I will briefly discuss our current state of the art in our work with respect to 6-point conformal blocks. So that's roughly the motivation for our line of research. And now I'm going to define 5-point functions, 5-point correlators. So you write this correlator in the following way. So there is some function that depends on positions, and then there are free sums that go. And then we have 5-point conformal blocks. I should say that everything I say today will be true in d greater than 2. So in d greater than 2, 5-point conformal blocks depend on 5 cross ratios. And so in this sum, Nij goes from 0 to minimal value of L, L prime. And the reason for having this sum is that here you really have a 3-point function of the following form. So you have operator with spin, then you have a scalar operator, then you have the other operator with spin. And then in this 3-point function, you can write several conformally invariant tensor structures out of the indices that you have here, and these all these tensor structures are taken into account by this sum over Nij. I'm going to define these cross ratios because, as it turns out, the choice of cross ratios plays a very particular role in everything I'm going to say today. So these cross ratios are defined as follows. Then U2 is proportional to x4 5 squared, but it can be obtained in a similar way, and V2 also should be straightforward to write. And then so you can see here that these two cross ratios, they are two usual UNV cross ratios for operators 1, 2, 3, and 4. And then these cross ratios over here will be again usual cross ratios for operators 2, 3, 4, and 5. And then there is this fifth one that whose meaning I'm going to describe in a second. And then the question is, what do we know about this 5-point conformal blocks? So these 5-point conformal blocks have been computed by several groups and several people. So I'm going to write their names. So it's Rosenhaus in 2018. Actually, before I get to that, so these 5-point correlators have been computed for the case where L and L prime is equal to 0 by several people. So only when you exchange scalar operators, we had quite a few expressions for these conformal blocks, and they are computed by Rosenhaus in 2018, then Parik in 2019, and Fortanma and Skiba also 2019. And all this, so they have written 3 different formulas basically for these conformal blocks that are consistent and that give the same result. And all their formula have one thing in common. You can write their formulas in the following way. So when you consider this, so you only have Nij being 0, and then their formulas are really 5 infinite sums. So you have 5 infinite sums with respect to each of the cross ratios, and these functions here are are given as the functions of delta, of 2 deltas and these parameters ni, and there are some hypergeometric functions and a bunch of Pochhammer symbols. So in principle, you have no chance to evaluate these sums analytically. You can do some numerics with it, but that's pretty much all you can do. But then if you want to consider spinning 5-point blocks, so in the case where L is not equal to L prime is not equal to 0, there are formulas written by David and Valentina in 2021. So they have given us the recursion relations of the following type. So you start with some spinning conformal block or conformal blocks for exchange spinning operators, and then you can express it as a sum of over deltas of scalar conformal blocks. Well, again, these coefficients are determined and they depend on, okay, I should say that these coefficients depend on D12, which is difference between delta 1, delta 2. They also depend explicitly on delta 3, and they depend on difference between delta 4 and delta 5. And also they depend on cross ratios. So now in principle you see that we can compute any conformal block. No, this is finite sum. This is always a finite sum. So in principle, we can compute any conformal block for any spins of exchange operators, because you start with David and Valentina's recursion relations. You express this block as a sum of scalar blocks, and then you evaluate scalar blocks using some of these formulas given here. So, but the problem, technical problem with this type of calculation is that on the ordinary PC, you can run this recursion relations up to spin 4 exchanged. So when you consider two operators, so okay, L prime equals spin 4. Because if you go to higher spins, then this recursion relations gets very complicated. They get a lot of terms on the other side. Even though it's still a finite sum, you get thousands of terms, if not tens of thousands. And then it's kind of computationally hard to evaluate these sums and to compute these blocks for higher spins.
Don't you have the NIJ index also on the right-hand side?
What?
The NIJ index of G. Yeah, on the right-hand side, you only have a G0.
Yes. So L is 0 here, because these are scalar blocks. So basically, this dependence on L is going to enter through these functions here.
And that's the thing that becomes 10,000.
No, you get 10,000 of these terms. So these are all scalar blocks with shifted conformal dimensions. But then you are going to get a lot of them, because this shift in conformal dimension is going to go from -20 to +20, and then there will be many terms. And then you can also shift external dimensions, and you can shift many parameters. Or you have to shift many parameters in these recursion relations.
So yeah, the NIJ is what?
It's still here.
It's in there too?
Yes.
Okay.
And the scalar block, then you still truncate it, so you don't have the full sum?
Yes. Well, if I want to compute numerically, if I want to evaluate numerically this conformal block, indeed, I can just evaluate this sum up to some finite order, and then I have computed all the scalar blocks with some finite precision, and then I can estimate these types of, I can estimate the values for spinning conformal blocks. That's definitely something you can do. So now I'm going, instead of use, so I should say that these coordinates that I defined here are defined in this Rosenhaus paper. And for that reason, I'm going to call them Rosenhaus cross ratios. So now, instead of using these, I'm going to introduce a new set of cross ratios. First, I'm going to consider the cross ratios of this type. So
sorry, can I just ask one question? So Vasco, I believe, also had an appendix with some algorithm, right, for computing any conformal block with spin?
Yes. You can use that algorithm, but the problem with that algorithm is that you have to do 9 infinite sum, if I remember correctly. Somehow they got even bigger set of infinite sums that you have to do. And there is, I will discuss slightly later why the conformal blocks that I'm going to present today are a bit better, and you can compute them more efficiently than their conformal blocks. The reason is that they didn't use the right radial expansion. for the choice of cross ratios. So now I consider a new set of cross ratios, and this new set was introduced in a paper of Ilya Buric, Lorenzo, Jeremy with Fokker Schomerus in 2021. So now so you can think about in these coordinates. So here I goes from 1 to 2. You have two sets of z and z bar coordinates, and then you have this w tilde coordinate. And using these cross ratios, the easiest way to think about 5-point correlators is in the three-dimensional subspace. So what you have is you have operator x free at infinity. Then you have operator x 4 at point 1 along this line, and then x2 is at 0. So you have three operators along one single line, and then the operator x1 lies in this plane. And then there is the other plane. Okay, I apologize. So x3 is at infinity. Then x4 is at 1. x2 is at 0. Then here is x1 in this first plane. And then there is the other plane. And operator x5 sits in this other plane. And then so then you can think about this z1 and z1 bar as describing the position of x1 on this first plane, and then z2 and z2 bar are describing position of x5 on this other plane that I didn't draw very nicely, but and then this omega tilde defines the angles between these two planes. So this is all in three-dimensional subspace, so it's easy to visualize, and omega tilde is related to the angle by the following expression. So now when you have z and z bar coordinates, a very natural thing to do in these coordinates is to try using radial coordinates, pretty much the same radial coordinates as we use for when we compute 4-point correlators. So these radial coordinates for 4-point correlators have been
are you eventually going to go back to these cross ratios? Is that a geometrical interpretation for W? If so, if you're not coming back, don't worry.
Yes, well, you can interpret, so you see here that W is related to W tilde by this relation, and then you can say that W is basically, that W is through W tilde related to the angle between these two planes. Because if you look at positions x1 and x5 here, you see that they lie on the opposite planes, and then you have this W that depends explicitly on x1, 5. Therefore, W must be related to the angle between these two planes. So that's the interpretation for the W coordinate. Thank you for that question.
No, but okay, that's not very geometrical. That's just saying there is a formula. I was asking if geometrically this W is... I mean, it has a geometrical meaning. Of course, there is a formula.
No, well, okay, this W maybe has a bit more geometrical meaning, but this W is directly related to the other ones.
Okay, so good enough.
Okay. Okay, radial coordinates for 4-point blocks have been introduced in a paper of Hogervorst and Slava in 2013, so 10 years ago. And the way to introduce these radial coordinates is the following, as many of you know already. And then here you have, so you have R1, R2, eta 1, eta 2. So you can think about these four these four radial coordinates as the radial coordinates on these two separate planes. And then the fifth one, which is the only non-trivial one, is given by the following expression. So then, yes, you get the W hat. So these radial coordinates, these are exactly the same as the 4-point radial coordinates. We didn't do anything here, but this one is I mean, you don't have the analog of this one in the 4-point case, therefore we had to be a bit careful how to define this one. And now when I have defined all these cross ratios, I can write the most general expression for the spinning 5-point conformal blocks.
Can you explain the motivation for this 1/2 minus W tilde? What's so special about W tilde equals 1/2?
W tilde. Yes. W tilde equal 1/2 corresponds to, if I remember correctly, these two planes colliding. Is that?
But doesn't really seem to be so.
W tilde 1. Yeah, then, okay. No, it's angle 45. It's exactly. Yeah, it's not. Yeah, okay. There is something. Sorry, I'm not very good with trigonometrics.
No, but this doesn't really explain why should you. What's so special about it being perpendicular?
Okay, on this level there is really nothing special. I will explain in 2 minutes how we define this. Why we have defined this new cross ratio in this way. Okay. So now you write the most generic ansatz for the 5-point conformal blocks in the following way. So this is what you have for 5-point blocks now. And okay, here you see that K goes from 0 to minimal value of J1 and J2. And then J1 and J1 goes from, so it starts by L plus M1. Then it gets lowered by 2 all the way to either 0 or 1, depending on the parity of the sum L plus M1. And similar expression you can write for J2 with just, instead with using L prime and M2, and everything else is exactly the same. So now you see that instead of having these five infinite sums that we had in the Rosenhaus expression, we actually only have 2 infinite sums. And when you fix M1 and M2, all these other sums are finite. So these are some Gegenbauer polynomials here. And you also have just the powers of this k. And this is, in some sense, the answer to the question that Slav asked before. Why did we define this w hat the way we did? Well, we basically noticed that when we define it in the way that's written there, we can just group all these terms nicely and have this nice expression for the conformal block.
I'm sorry, Peter, you're not really answering the most puzzling aspect of this formula. Why for w hat equals 0, you only have 1 term in that formula?
W hat equals 0?
So if w hat equals 0, you only have surviving k equals 0 term.
Yes.
So,
well, that's
so
only in this one formula.
So there has to be something special about w hat equals 0. There is a huge decoupling of terms for w hat equals 0, but why should there be this decoupling of terms if the planes are perpendicular? There's something that you are not, you're hiding from us, some miracle.
Well, let's see. I mean, but you still, well, what is happening is that many of these tensor structures decouple. Many of the tensor structure of descendants, of spinning descendants decouple. Okay, but it's not, you're not saying really that descendants decouple, because descendants do not decouple. There is still sums over J1 and J2. So descendant operators are still there, but some of their tensor, or many of their conformally invariant tensor structures, so yes, when you look at this 3-point function, these 3-point functions with 2 spinning operators, so many of the conformally invariant tensor structure decouples. That's true, and I am not really able to tell you why at this stage. But it's not that all descendants decouple, and then there is some it's just that some of their tensor structures decouple. Okay. If that was something that was maybe bothering you.
Okay.
Can you comment on the case in which all 5 points are on the plane? Then you should just have 2 pairs of independent cross ratio, but
then
you still have 5.
Yes, that's why I said I'm always, well, I mean, okay, you can take w hat to be whatever it is in that case. And right, I mean, then it's, yeah, then it's just a number, and there is nothing, I mean, there is nothing special happening there. And I mean, I said already that I only consider cases where we are in D greater than 2. So yes, I do not consider the cases where you do not have this cross ratio at all. Then these answers would not work. These answers would probably not work in 2D. Okay, so now I'm going to remind you how the 4-point conformal blocks look like in the radial coordinates, and then maybe we can discuss the relation. So 4-point conformal blocks look something like this. So there is, again, there is one infinite sum that goes from 0 to, again, to 0 to infinity, and then there is the other sum over J, where J is given by, so there is coefficient CMJ, and then you have Gegenbauer polynomials. And in this case, J goes from L plus M minus 2. Again, it lowers by factor of 2. It lowers by 2, and then the lower bound is given by maximal value of L minus M or mod L plus M comma 2. So okay, I should say that these C coefficients are so far undetermined, and I'm going to describe in 5 seconds how you can, in 5 minutes maybe, and how you can determine them. But now, if you look at this, so if you look at the range of J's here and the range of J's here, you're going to notice that there is a small difference, and that difference is in the lower bound for these sums. So J's in this case can be interpreted as the contribution of a descendant of a primary operator with spin delta and with conformal dimension delta and spin L, and then you have a descendant of the order M and spin J, and so this contribution is literally the contribution due to that descendant. While here, so that's why you must have this type of lower bound, because, for example, if your primary operator is of spin 4, and then you have, if you have primary operator of spin 4, and then if you are at order 1, so you're only taking one derivative, the lowest spin you can get is free. It's not really 1 or 0 as here. So the lowest spin is free, and that's why you must have this as a lower bound in this case. So that is really telling you that these J's are not really J's are not really the descendants of the spins of descendants in the 5-point case. They might be related to these spins of descendants, and we strongly suspect they are, but in order to find that exact relation, you would actually have to act on this ansatz with the Casimir of SOD subgroup, and then to diagonalize that action, but then in that case, your ansatz would not be as simple as this one, so we believe that simplification of this ansatz is maybe more important at this stage. So, and then on the same footing, there are, so in the case of 4-point functions, if you consider all identical external operators, then you get that, then you conclude that only coefficient C mj can be non-zero if m is even. But there are no such selection rules for the 5-point function. So if you consider 5-point functions of all identical scalar operators, you're going to find that all C coefficients are in general non-zero. So that's why it's still a bit harder to compute these 5-point correlators than 4-point ones, but I think we might be on the right track. Now, as I said, the advantage of this ansatz is that there are only 2 infinite sums instead of 5s, and this is the first way to treat all 5-point conformal blocks on the same footing. So now you don't have to run these recursion relations anymore, and you can just compute, you can just analyze this one, analyze this ansatz, and then compute the C coefficients. The way to compute these C coefficients is basically to solve 2 quadratic Casimir differential equations. That's the only thing you need to do. You don't need to worry about quartic Casimirs and these differential operators that you get from vertex operators. So in these coordinates, quadratic Casimirs look something like this.
Can you comment on something like, so in the 4-point conjunction case, one reason also to introduce these radial coordinates was to map the region where the blocks are analytic on the unit disk. So in your case, what are the ranges of various coordinates where you expect the blocks to be analytic functions, smooth functions? Yeah.
That's much harder to say in this case.
Why harder? I mean, we know that it's all related by some operation. Since you're doing OP into channels, you just need to pay attention to
right, but you have 2
spheres
planes.
not to overlap.
I mean, you have 2 planes, and then you can think about, so if you start thinking about radial coordinates on one plane in the same interpretation as you had for the 4-point functions, then these two planes are kind of coupled, so you cannot decouple them and think about radial coordinates on one plane and the other plane. You actually have to consider the fact that these planes are connected and that transformation on one of them affects the other one, especially, yeah, if you do anything to this x2
But
and
there is
x4.
there is a general criterion for smoothness of conformal blocks. It just says that if you have to find some spheres which separate these 5 points into
Yes,
2 points plus 2 points plus the third point. You just have to see what this equation means in terms of r coordinates and w coordinate.
Okay, I can tell
It's a
you
geometric problem.
where this sum converges. I can tell you that.
Okay.
So if you fix, okay, let me first tell you how to compute the C coefficients, then I'll comment where it converges.
Okay.
So you're computing the C coefficients by just using the two quadratic Casimir differential equations. You plug these ansatz into differential equations, and you're solving this equation. And then one good thing with the choice of our coordinates is that, so if you want to compute coefficients at order m1 and m2, and then you plug this, so C with some fixed m1 and m2 and all other parameters varying, then you plug this ansatz here, and then you expand this Casimir equation exactly up to that order, m1 and m2. You get just enough constraints from two quadratic Casimir differential equations so that you can fix all C coefficients. And then you can just compute, well, pretty high number of these coefficients. Of course, there is a more, everybody that knows anything about conformal block computation will say this is not the best way to compute them, and that would be right, and I will comment on that later. So these functions Ri here are rational functions of quantum numbers and cross ratios, so these are just rational functions. There is nothing irrational in them, and that's also why this choice of W hat was particularly convenient. And then, to answer the Slava question, if you fix W, if you fix W hat, eta 1 and eta 2, and then you say that R1 is equal to R2, then you're going to find that this sum converges for all R, so let's call this R, for all R's which are less than the R that you're going to find by considering this equation. For, yes, all R, okay, when you consider this equation, you might get complex R, but you need to take all R's that are less than the absolute value of the R defined here. So maybe that's better. So what that means is basically, yes, if you fix, so you fix all these angles, and then you're taking some symmetric limit where, then you're varying these R's, then the blocks are going to start converging when x1 gets too close to x5. And then, so you're writing the OP, this one here and this one here, and then these types of OP will stop converging. So when you hit that point, you have to, the blocks are just going to diverge after that. Now, you might notice another thing. If you look at this formula here, there is no Nij dependence on the right-hand side. So you might be wondering, did I just lose the quantum number? And I really did not. The Nij here is going to enter through the initial conditions. So if you consider the scalar box, the standard box basis of the conformally invariant tensor structures in the 3-point functions, your Nij So then your Nij is going to enter this formula through the initial conditions. So initial conditions are when you're at order 0 in M1 and M2, then turns out that you can solve all other C coefficients through Casimir equations at this order, except these, except this number of C coefficients, and then you notice that this is exactly 1 plus minimal number of L comma L prime. That is exactly this number of unfixed coefficients at order 0, and the choice of this, so the way to fix these coefficients is basically determined by this quantum number Nij. So Nij enters through the initial condition in this equation, and then, as I said, you literally only need to worry about 2 quadratic Casimir differential equations.
You say that you didn't have a clear interpretation of C with respect to descendants and so on and so forth. So where is this boundary condition coming from? Maybe you meant a triangular.
Okay, yes. Well, so what is when you are at order 0? That's really you're really taking R1 and R2 to be very, very small. So your block is actually given by the block in the OP limit, and then you take your 5-point function. You write this function in the standard box basis by taking the OP limit here, and you're going to get some expression. Then you match that expression with the expression that you get for your conformal block. So that's the way to fix these C coefficients. Now I'm going to apply this technology to the mean field theory, or at least to show you how it can be applied to mean field theory, and there are new non-trivial results to get even on the level of mean field theory by using this method. So what we did in the mean field theory was we considered the correlator of the following type. So we considered f phi phi, then phi of course all of them are inserted at different points, so I won't denote them. And again, I'm using a standard mean field theory notation that you probably all know. So when you consider this 5-point correlator, you can compute it explicitly in mean field theory from one side, and the other thing that you can do is you can expand it in the OP expansion, OP expansion, and then if you consider the OP limit of this correlator at R1 goes to 0 and R2 goes to 0. At each fixed order of R1 and R2 in this limit, there will be just a finite number of primary operators contributing to your 5-point correlator. And you can exactly tell which operators are going to contribute, because you see that R scales with delta, so it's an easy exercise to see which operators contribute. And then you can compute many OP coefficients for these operators. And then in the end of the day, what you get is the following product. So you get, so I mean, the way to do this exercise is to compute as much as OP coefficients for as much as possible operators. And then when you do that, you kind of notice a pattern in these expressions, and we were able to write the general formula that's true for all n and else of this NL, and then N prime, L prime, and Nij. So we were able to find this most generic formula, and this is a new result in mean field theory, because so these OP coefficients, this one here and this one here, they were known before. These OP coefficients here were known for n equal n prime equal 0. They were computed by Antonio Antunes, Costa, and others in their paper about LightCon 5-point functions. But then we were able to find all these other coefficients. So this kind of shows you that there are new results even on the level of mean field theory to get through this analysis. Sorry? Some prime, I'm sure I do. Better. Okay, so now I'm going to discuss the numerical part of conformal bootstrap that we have done. So the question is, how do you do bootstrap for 5-point correlators? So you can do a following thing. You write your 5-point correlators as this. So we consider only this type of correlators, where these two are identical, these two are identical.
Sorry, before you move to the numerics, but is there no punchline here? You just said we compute something. Is this useful for something?
I mean, this formula is given explicitly in our paper, so this is new formula for all these OP coefficients that were not known before. So the point was that you can just get new results even for the mean field theory by studying 5-point, and then for 6-point functions you would be able to compute you would be able to do the computation for Nij, yes, for this operator having arbitrary n.
And then the expectation is that there is some universality for any CFT for some range of parameters, I assume, right? That
I would not be able to confirm that.
The usual Reggie theory, right? When they are separated.
Maybe.
Was it the case or not that before phi with phi NL, it was the universal behavior as soon as?
I mean, this is all mean field theory. We don't have anything beyond mean field theory. So, I mean, yeah, this is all mean field theory. So we only have coefficients in mean field theory. We don't have any perturbations to mean field theory, if that's...
Okay, that's...
and, I mean, maybe before I go on, I can say another thing here. So if you look at these 4-point blocks, and then you look at these 5-point blocks, it turns out that they kind of have similar structure. So it's in some sense easy to guess what would be the 6-point conformal, how you can write 6-point conformal blocks. And we were indeed able to do that. So you can write 6-point conformal blocks in the snowflake channel. Now Pedro's question reminded me about 6-point blocks. So,
but are you sure you want to go to 6-point block? You don't have much time to discuss numerics.
Okay, I guess you can do it.
We got the point. I mean, we got the point.
It's kind of obvious that you have 3 of these R's, and then it's exactly the same. Instead of 1 Eigenbauer, you have 3 of them. In that case, you have 3 of these, and that's exactly the right number of cross ratios, and they have the same structure. Okay, so numerics. We consider this type of correlators, and then we do the OP here, and then we match it to the OP here. But now you see the problem. There is no positivity for the 5-point blocks because we have products of 3 OP coefficients, and there is no way to write any positivity constraints. But instead, we are going to use the method developed by Gliozzi in 2013. the method that does not require unitarity of your theory, therefore does not rely on the positivity of the squares of OP coefficients. And that method, we're going to use the generalization of that method. Gliozzi, of course, applied that method for 4-point functions, but we are going to generalize it for 5-point functions. Now you can write the crossing relation here, and then what you get is something like this. So you get sum over primary operators that are not identity, and then 1, 1, 0, so here you exchange U with V, then there is W. Then you divide all of that by identity contribution. Identity 2. And so this is the crossing relation. And now what can you do is you can truncate this this equation here. So instead of considering sum over all sets of primary over all pairs of primary operators, you just say I'm going to consider finite number of primary operators here. And then the other thing that we do is we are going to fix all the CFT data that we can get from the 4-point function, so that we minimize the number of variables that we have in our 5-point computation. And then what you can do, since this equation has to be true for all choices of cross ratios, that means that it has to be true on a functional level, so you can take really derivatives of this equation. And then I'm going to just write it like this. So then you get the requirement that all derivatives of this equation have to vanish, and then I'm going to denote these equations that I get by taking these derivatives by the following way. And then we are going to evaluate all of these derivatives, and we are going to evaluate everything at the following configuration, where U1 is equal to U2, V1, V2 equal to 1, and W is equal to 3/2. And this is the case where R1 is equal to R2 is equal to 3 minus square root of 2, and in radial coordinates, W hat is equal to 0. So in this configuration, our conformal block converges very quickly, and as we discussed already, this is the configuration where these two planes are orthogonal to each other. And then what can you do is you can pretty much take any number of derivatives here, and then this equation has to be satisfied for all of them. But since you are doing the truncation, since you're truncating here, it really cannot be satisfied for all choices of derivatives.
Can you explain why one user equal to 1 and not, say, 1/4 as we usually do for the 4-point function?
Because this is where blocks converge way more quickly than in that case.
Yeah, but why?
I would not. Well, I guess. Let me see. So in the 4-point functions, what you do, but when you take all cross ratio U1 and U2 to be 1/4, you get points on the square. But in our case, we actually get so our case is such that we get these points to be equally separate. So this is distance 1, this is distance 1. This is also yeah, this is not a distance 1. This is, I think, distance square root of 2, and then. So I think it translates to the very similar configuration in our cross ratios. It's just that our cross ratios are differently defined. So you still have kind of square, except that you break this square and you have two planes on this square. If you want that yeah, this is some hand-wavy geometrics, but really what we did was that we evaluated these equations for many choices of cross ratios, and we observed that here they converge way better than at any other
So I
choice.
just want to say, what would happen if you take u equal 1, so r parameters would become smaller? So why should the equation converge slower? I don't understand.
Yeah, that's a good question.
And w hat, so we still keep w hat 0, so nothing there changes. And in the cross channel, you just exchange ui and vi. So if r was small, it's
I
going.
think what's going to happen in that case is that these two are going to collapse actually here. I think we tried that at one point, and then x1 and x5 actually collide on this plane. Yeah, on this line here. So it's a bit non-trivial. Yeah, it's a non-trivial choice of the configuration. No, this is total. Yeah, 2 minus square root of 3. Yes, of course. That's a bit smaller. So, okay, now I'm going to do this for the free theory.
So just one question. Is it true that this particular crossing that you chose, this channel, maps UI to VI or not?
Yes.
Okay.
Yes. So you mean this piece? Yeah. And okay, here, this is really x2 exchanging with x4. So you exchange 2 points that sits on this line that I plot before, and that just changes the definition of UIs and VIs and doesn't affect planes, definition of planes itself. Thanks for that question. So in free theory, I'm going to truncate my expansion by just including the following operators. So I include phi squared. I'm going to include operator of spin 2, also known as stress tensor. And I'm going to include operator of spin 4. So I'm doing all this computation in free theory. So this I will call C. So this is all in D equal 3. And this is literally the free theory. And then the unknown parameters that I'm going to have in my computations are t phi squared t. So there is just one of them that's not fixed. The other ones are related to this one by word identity because the stress tensor is conserved current. Then I have t phi squared c. Again, I only have one. And then I have c phi squared c. And here I'm going to include all of them. Even though you can say, okay, C is still a conserved current. Everything is conserved current in 2D in free theory. But I'm not going to treat C as a conserved current. I'm not going to use the word identity for the C for this operator. And then also, I'm going to treat delta phi as unknown. And the reason for that is that I do that just because I can. Because my conformal blocks do not depend explicitly on delta phi, as conformal blocks depend only on difference between 1, 2, and 4, 5. Therefore, delta phi do not appear in conformal blocks, and I can still compute them very precisely. It's only these functions p that depend on delta phi. Therefore, I can include this dependence free of charge. And then what I do is I write a cost function of the following type. So this is total number of unknown coefficients is 8. So I define cost function like this, where I have some numbers Ri here, and then equations I squared. And then these Ri's are, so these are positive pseudo-randomly generated real numbers. And then in order to compute this unknown OP coefficients, I'm just going to minimize this cost f function. The set of derivatives that I'm using in order to write down these equations is basically all derivatives up to free derivatives. So I start with not taking any derivative at all, then I take derivative with respect to u1 and so on up to, so free derivatives here, then u1, u2, b2 and whatnot. So all the way up to 3, I take all derivatives up to 3, and that gives me total of 18. I get total of 18 independent equations EQI. And then I just use these equations. I also write this randomly generated real numbers, and then for each set of these randomly generated real numbers, I find the minima of these functions for this coefficient, and that is the result for these coefficients that I get. And then I'm choosing out of these 18 equations, I'm choosing the sets of those that are going to give me delta phi closer to 1/2. Because I know that 1/2 is the exact value for this delta phi, and therefore I can put that requirement. And the reason why I have to put this requirement is that instead of, when you compare this computation to Gliozzi computation, he does all of his technology for the 4-point functions. Therefore, he's sitting in space of two-dimensional space of cross ratios. And then in that space, it's easier when you do this truncation, you are actually closer to satisfying this equation. Basically, you're making less error in that case. And also, there, when you truncate, when you include t, so when you include operator t here, you are done with the operator t. While here, even though I have included stress tensor here, I'm just taking the pairs of stress tensor with this one, with itself, and with this one here. Then t also enters on this side with other operators. Therefore, my truncation will arguably work less effective in this case. Therefore, I need additional constraint, and this I use as an additional constraint when I'm choosing these derivatives. Then, in the end of the day, what I get is that t phi squared t 0 is given by 0.52. I should say that this estimates, so the way I estimate the error bar is just by doing this computation for many choices of this randomly generated real numbers, and then I just find the standard deviation of the distribution. So this is not really rough. This is not a very precise way to determine error, but what we know is the right number. It's this. So this is roughly 0.533. So we are kind of close for that one. Then we get two more. Two, 1, 2. And this exact value is 1/32 square root of 5/2. So that's 0.2264. And the other one that we get is this one, 4. So 0.3. Well, the exact number is square root of 2. So that's roughly 0.221. So, okay, so these are three OP coefficients that we can compute more or less with relatively small standard deviation and more or less accurately. The rest of them we really cannot compute accurately, and the way to see that is, for example, if you look at one of them. So let's say lambda c phi square c for Nij being 1. What we get is that we get a result like this, while the exact number should be minus 35/16 square root of 2, and this is minus 1.5467. So here you kind of see immediately that this standard deviation is order of magnitude larger than the one here. So these coefficients are way more scattered than these ones, and therefore we really cannot compute them quite precisely. And the reason for that is that the truncated, since this is free theory, we can basically test everything. Truncated theory, when we do truncation, the contributions due to these operators at this particular configuration is the same order of magnitude as the error that we are making by doing the truncation. So there is no hope that you can expect to compute these OP coefficients, and the indication of that is this large standard deviation. Then we do the same thing for the 3D critical Ising. So in this case, we truncate our expansion over primary operators by just including these contributions. So, and now you see kind of the reason why I didn't assume this C is conserved current, because my goal was to do this same computation in 3D critical Ising, and here this C is not a conserved current. And when you repeat the whole procedure, now it turns out that you have more unknown OP coefficients, because on top of these that I have written before, or their analogs, you actually have two more. So you have epsilon prime, epsilon, epsilon prime, and you also have lambda, epsilon prime, epsilon c. So now your number of equation is equal to, number of unknown variables is equal to 10, and then your cost function has to include 10 or more equations. And when you do the same computation, you get something like this. So these are the same free OP coefficients that we were able to compute accurately in the free theory, and in this case they are given by this, and the rest of the OP coefficients we really cannot compute very accurately. And I should say a few things here. So the value that we got for this OP coefficient is below the bound that was set by Cordova, Maldacena, and Turiaci in 2017. So they set a bound for this OP coefficient in the 3D critical Ising model to be less than 0.9810 in our, this is all in our normalization. So this is Cordova, Maldacena. So the value that we computed, of course, satisfies this bound. And even more interestingly, recently this value has been computed by other group that studied this fuzzy sphere regularization in 3D critical Ising model. And the value that they got in our normalization is given by the following number. So they got 0.805765. I guess we'll hear more about this in the third week, but seems like these two numbers agree quite well, and yeah, with the only caveat that their error bar is much smaller than ours. So that's pretty much all I had to tell you. There are many things to... Sorry? How they estimate the error? How do we do that? Well, because we do this choice, we choose many of these pseudo-randomly chosen real numbers, and then you expect that. So if there was no truncation, if you didn't do truncation in this function, in this EQ functions, then for every choice of equations you would get only one number. minima would always be the same. Minima of cost function would always be the same. But since you did the truncation, then when you pick different choices of these weights in the cost function, then you are getting the spread of your result spread, and then we take the standard distribution, standard error of that distribution, basically, as the estimate of the error bar. So again, this is not very sharp and very precise result, so there is a possibility that we are wrong, but well, first results indicate that we might not be. So yeah, there are many interesting things to be done in future here. For example, to study 5-point conformal blocks, and in particular study them in comp channel. Hopefully we'll have some results there to report soon. Then you can compute 5-point conformal blocks by writing just recursion relations for C coefficients instead of solving these Casimir equations order by order. And that is something that we have done right now, and hopefully that's also going to come out soon. And then here you might be tempted to consider some other OP. So in the case of criticalizing, you might consider the OP between sigma and epsilon, and then you might get additional constraints. So you might be able to improve some of the bounds that we have. Then you can bootstrap many other correlators, many other theories, and hopefully this is just the beginning of an exciting journey of bootstrapping higher point functions. Thank you.
Thank you very much. I guess there's time for one quick question. Yeah.
Yeah, so with this Yahtzee method along the years, like there's small variations, and we've tried more or less everything. And okay, there's Yahtzee use determinants, then I don't know, we use the minimal singular values. Now you're using this function. Last year, Marco Serone put out some Monte Carlo related approach. Did you try all of this and then you went to the function because it was better? Is there some, like, what should we do to save this?
It's not clear. Yes, that's an excellent question. I forgot to mention that there is really a series of papers here that generalize this Yahtzee method. But it's not clear which one is the best. We found this one to be particularly good because we could get these numbers in free theory. But yeah, it's a priori not clear why this method is any better than any other. We tried most of these methods that were already available in literature, and then we settled with this one. So yeah, it's not clear at all. That's a very non-trivial question, how to maybe improve this method. Yeah, one way maybe to improve this method would be to do a truncation here, truncate just finite set of primary operators, and then approximate all these other operators that you are not including by mean field theory, my mean field theory OP coefficients, basically. So that's one idea that we are trying to work on, and hopefully we might be able to get some better results by doing that.
Thank you. Okay, so let's please thank Peter again. So let me